So, well, Matlab is going to be basically the focus of today, but not entirely, because we will not use basic Matlab only. It's just a 1/3 of our need for Matlab. There are two other toolboxes that are fairly important to us, so I'm going to discuss them too, and then we will conclude hopefully today. So, yeah, for the beginners, this is going to be basically the interface that you will be greeted with. And I recommend you to use the basic Matlab interface because it helps you out in informing you about the workspace, about the history of your commands, about the command window. And it has tools that can just make life easier for you. If you're an advanced user, as I like to call myself, I tend to use VS Code for Matlab, and I just want to quickly show you that there is an extension that is quite useful for this purpose. Of course, VS Code does not directly come with Matlab compatibility, but what we can do is we can use a Python interface in order to open up a Matlab session on VS Code. And since this is a dark theme and since it has some editing capabilities, I like to stick with VS Code. It is easier to open up a PDF, a Matlab file, another Matlab file, and something else maybe. So if you're interested in this, if you're an advanced user, the only downside to this is basically it uses a earlier version of Python. It should be a 64-bit Python package with 2.7, 3.7, or 3.8, which are fairly old now. If you download one of them, or if you have Anaconda, for example, you can move on to the next one. The second requirement is quite easy to meet because it's basically a new Matlab version, so that's not a big deal. Once you have installed the Python version compatible with this one and you have a new Matlab, you can just go ahead and basically install this Matlab engine API for Python. If you are looking for instructions, what you can do is you can just click here and it will pop up a new window which explains how to install this API for Python. You have to browse to this exact folder and then call this Python command and you should be good to go. Basically, you should install the Matlab engine. So you can check out the documentation here. Once you have done that, there are also some neat other extensions that help you out in maybe editing and having the styling, also maybe the linter. There are some capabilities that you can add to your VS Code, but this one is the essential toolbox that you or extension that you should look for if you are going to use VS Code here. Once you have VS Code, what you can do is you can just have basically a Matlab file, and then you can just create a Matlab session. Now, once you've downloaded and set up everything, there are 3 different options to run Matlab sessions here. One of them is to open the Matlab terminal, which I use most of the time, but there is also a run current Matlab script, which corresponds to F5 in Matlab, and then also a selection that you can run in Matlab, but I like to use this one here. Now, the downside, another downside is that once you have a certain code here, for example, let's say a is equal to 2. This is basically my Matlab here, the terminal Matlab here. So if I run test, you can see it just runs, and I have basically a equals 2. Now, when I update my script and look for a, it's still 2, but when I run it again, it updates now. So I have to run it twice in order to get the effect. And that's another downside. And the reason for that is because we have a interface from Python to Matlab and then from Matlab to Python back. So basically, this is not a Matlab terminal at all. This is a Python interpreter that acts like a Matlab command window. So therefore, there's a downside to it, but I'm used to it, so I like to do this on VS Code, which is just an advanced topic. Now, this doesn't matter if you're a beginner and if you don't want to use or have to use VS Code. You're just in Matlab, you open up Matlab, and then you can just code a is equal to 2. That's it. So let's start with our Matlab introduction. Well, if you're familiar to any programming language, especially C, then using Matlab is um, a very good experience, at least, because it gets rid of the whole difficult syntax of C. And the reason for that is its purpose. This Matlab interface, this programming language, is developed for efficiently prototyping and quickly developing stuff, or maybe examining theoretical aspects. Therefore, it has this flexibility, this easiness. It's a kind of a simplified language in most of the ways. So yeah, when you're, for example, defining a new variable in C, you have to do it like this. You have to give it a data type, you have to give it a name, and then the value. But what Matlab decides to do is it looks at the value itself. In C, what you can do is you can just skip the value and then define something as a variable and give it a name, and that's going to be it. But that's not possible in Matlab. You cannot just have the name of the variable and then enter it if you've not defined it. You can see it's not a recognized variable because this doesn't exist, and you cannot define it like in C without a value. And the reason for that is to just skip the data definition, data type definition. You don't have to say double C and then maybe assign it 2.2. You can just skip the whole thing here. You can just say it is going to be double because the value itself is given in double. So you just have 2.2 and it decides to define it like double. By the way, all numerical stuff, you can see I have called clear, which got rid of the whole workspace. So I've defined A, B, they all live in the workspace. So you have kind of a visual RAM here, which helps out. And you can also see that this is basically an interpreted language. We didn't hit run or we didn't hit compile or anything because we don't compile here. It is a interpreted language, which means that if I input something, that will basically convert it into machine code on the fly. So basically, this is a Python-like language. And for certain cases, if it's necessary, what you can do, and that's the beauty of it, is you can develop everything in Matlab. And if there are compatibility issues, that's going to be resolved and stuff. But other than that, you can just compile that back into C. You can just see the C equivalent code that you needed to generate. So that's the beauty of it, because you can then go on and deploy it onto a certain hardware or somewhere where it should run with performance. But here Matlab doesn't concern about that. So we don't really think about performance. We just want to prototype stuff. We just want to test stuff and see the results immediately. Therefore, we don't have data type definitions. That doesn't mean we cannot enforce variables to have certain data types, but by default, we don't really need them. So if I run clear, you can clear the workspace here, which you can also do by right-clicking it, as far as I remember. You can also clear the console by using CLC. So you can just CLC and gone is everything that we have written here. So you can just clear up your mind, basically, what you can do here. Now, if you have defined A equals 2 by 2, what you can ask for is, what's the class of this? What is the data type of this variable? Well, it tells you it is double. We don't have float, we don't have integer, we have double. Even if A, let's give it another name, if it's an integer, if you ask for the class of it, it's going to be double, because precision is important. With data type conversion, we don't really deal with that. We just assume that all numerical data is double, and you can just have the highest precision that is available to you by default. Now, once we have the understanding of variable definition, we can basically see that there are also some similarities. Basically, when we have a character, what we can do is we can use the C style here. So it relates to C most of the time. You can see that single quotes A is basically a character. And if we ask for the class of it, it will give us the result. It should be C. It's char, so it's a character basically. And if you think about multiple characters, we can also do that. And if we ask for the class, it's still going to be the same. Now, this corresponds to basically char, temp, and then a square brackets, and an ASD. This would be the C version here. There's a typo. This would be the C version, but here we just use single quotes, provide the stuff, and we don't really have to say that it is an array, even though if it is an array, basically. It's a character array. So yeah, when we have character arrays, one of the things that comes up to my mind is what would this command do? Because I have ASD, I have BCD, and if I want to somehow sum them, what I mean is I want to concatenate them. I want to just build a longer text that consists of these two pieces here. But the interesting thing that will happen is that if I enter here, I can see that, well, basically this was not expected. I wasn't expecting to see random numbers when I do this operation here. So yeah, if you know what a character is in C, you would know that, for example, A is going to be, let's say 3. Let's assume there's no null termination. So let's have B, that's going to be BCD. Now, if I want to add them together, first of all, I need to loop. So what I need to do is I need to access the first one. I should add the second one to it, and then assign it to another one. So you can see that we're basically avoiding so many things here. If we wanted to use C, we needed to do this for 0, 1, and 2 because the length of 3, etc., etc. So this would be everything that we should write down to kind of do this operation where we didn't even define any variables, anything, and we just told Matlab what we wanted to do. But if you know C well, you will see that this is not making sense because this is literally what we do here. We take A as a character, we take B as the character, and we then try the sum operation. And the reason why this works is basically the ASCII table here. This here. Now, if we are talking about a char data type, what we are actually assuming is that it is an 8-bit, 1 byte data type. So this means that we would have 1, 2, 3, 4, 1, 2, 3, 4 zeros, and 1, 2, 3, 4, 1, 2, 3, 4 ones, and we would address 256 different things, basically. Now, we also have unsigned char and char, so it means that we have sign here when we are talking about char. So it would be a 7-bit data. So that would give us 2 to the power of 7, 128 different things to address. And here in the ASCII table, you can see we have 0 in decimals. It goes up to 127. So there are 128 things. So what these things are basically all the American letters and the characters on an English keyboard, what you can get as characters. There are also some additional communication stuff embedded in here because this is an old standard and that was necessary, so they added it. Today we don't really know what start of, well, we know what start of text, etc. is, but this bell here, for example, kind of lost its meaning, but it's still there because it's an old standard for backwards compatibility. But what we're more interested in here is basically the character A, the small letter A here. It's 97, and then B, that's 98. So when we're basically defining a character, what we're defining is basically a 7-bit value or 8-bit value with sign. So if I do something like this, for example, if I add 1 and subtract 1, you can see that it wouldn't change the result, and it would give us 97. And 97 is basically the decimal value of small a here. So we're dealing with numbers, even though they look like characters. So that's the basic idea here. And when you do some arithmetic operation on them, plus, minus, multiplying, and stuff, then Matlab just converts them into decimals or integers, or basically into doubles, because double is the basic numerical data type in Matlab. So you can see that when we have a plus sign, even though we have characters, if it's convertible into double, it will immediately be converted into double. And this is the reason why we get 195, 214, and 200 as values, because this is not an ordinary operation. This is basically the following. It means that I want to add A, S, D, and B, C, and D. Or we could also do the following, 97. So this is 97, and then we have basically 98. We could just do the same. And this would be 99, this would be 100. And then I guess this one is also 100. What was S? Let's look it up. So S is going to be 115. So this is basically what's going on. Even though we are giving a vector of characters, when we have plus sign, we're just adding them together. Now, there are two things. First of all, we have seen how to define vectors in this case, because if you are defining it as a C character vector, you would use something like A, and then you would give it a size. Now, these square brackets have a meaning, and in our case in Matlab, it means that when we use square brackets, we're defining arrays or vectors. So that's one thing. Since we are dropping this data type here, what we do is we just put in an equal sign here to the name, and then we just plug in the data, because, well, we are operating based on value. So therefore, we need to do this. These commas are not really that important, but we also have them in C. So yeah, that's kind of the way that we deal with here. But the meaning of this comma is basically it's going to be side by side. So that's important to know. But I highly recommend you to use commas, because accidentally, when you have a space there, when you copy and paste it to another place, you might get rid of the space accidentally, and then you end up in a whole different array here. So you can see that we can define arrays by using square brackets, accumulating the values, separate them by comma, and you're good to go. So Matlab does some data type conversion, as you can see, but what if I wanted to really do this concatenation of strings? Because I have character arrays, and in C, we all know that this is a big headache for us. But once we use the C string library or the std string in C++, then everything becomes much easier, because they have kind of this data type that is not a character vector anymore. It has some string capabilities. So in Matlab, we have that same thing. And you can also think about the std string, if you know what it is, because it's kind of the same concept. You can have double quotes AST and single quote AST, but the difference is the following. I can now do this concatenation operation based on the plus operator or the addition operator. So this is quite important to note, because it kind of tells us this following thing. If you are going to use some string manipulation, if you're going to dive deep into the string territory, you should use double quotes. So no discussion there. But if you just need an immediate string, and then you're just not going to do anything to it, and you're not going to manipulate it, you're just going to show a string somewhere on the graphical user interface, on the command window somewhere, then you can just feel free to use single quotes. But if you use single quotes, you might end up in problematic outputs. You might end up in errors because, well, those are not characters. Those are basically numbers. But if you just want to display stuff on the console or somewhere, just use single quotes. But if you want to concatenate them, if you want to, for example, search a substring in a string, use double quotes. So that's basically the idea here. Since we've seen how to define vectors like this, this is not the only way of defining vectors in Matlab. There's also another separator that we use in Matlab, which is basically this semicolon. And what it does is it's basically the transpose. So this is a column vector. So this is a row vector. So when we're talking about row vectors and column vectors, or column and rows, we're basically talking about 2D space here. And it means that we are actually talking about matrices. And the name also implies that it's called Matrix Laboratory. Therefore, it's Matlab. So it originates with the purpose of developing a tool for matrices. If you know C, and if you try to have matrices in your computations, what you most of the time do is either you just pick something up on the internet that is already developed for you, a certain library, or you just sit down and write your own code. Basically, what Matlab did was basically the same, but they developed it into a language. And it came to its days where it is quite powerful as a tool. Now, we're talking about matrices, and it originates from that. So therefore, we will have most of the time the data type double with matrices. Even though I'm saying it's a vector, it's actually a row matrix. So therefore, I can also use commas and semicolons to generate a column vector or a row vector. So it's quite important to know this stuff, because what we can do is we can do stuff like this. We can have two row vectors now, 3 and 4, and we can stack them into a matrix, let's say M. And I don't want to have them side by side, even though I can, like this. It would grow into a 4-element vector here. I want to have them like this. So just place the first row and underneath the second row. So I built up a matrix. And if you look at the notation, it kind of gives you away that you're just having this one here, and then 3, 4. And in Matlab, what we can do is we can just drop these internal square brackets, and we can define our matrix like this: 1, 2, 3, 4. If you have commas, they will be side by side. And if you have semicolons, they will be on top of each other. So basically, we have the row, and then go one line down, have the next row. So this is basically the way of defining matrices in Matlab. Another alternative way would be to have column matrices like this, 2 and 4, and you would stack them side by side. So A, comma B, and it's going to be the same matrix. So knowing what a comma or a semicolon does, or what square brackets stay for, is important in Matlab, because this is the very, very basic of Matlab. So if we repeat the last step that we've done by copying and pasting stuff like this, like A was this one here, B was 2 and 4. It still works, of course, but if we delete the internals here, then we get into trouble. And this means that basically, comma is basically calculated first, then the semicolon. What I mean by that is the following. Even though you are reading it like we have 1, then go one line down, 3 and 2, and then go one line down, 4, it doesn't work like 1, 3 should be together and 2, 4 should be together. It is basically starting with the commas. So therefore, this is not a valid usage. You cannot define this, because it will interpret it like these 3 individual pieces, and it will try to stack it on top of each other. So, and the size does not match because each row should have the same size, or each column should be in the same size in order to be able to stack them together. And you can see if I would delete probably the value 2 here, I would solve the problem, or I should add numbers to 1 and 4 in order to have the same size, in order to be able to define the structure here. So what I need to do, I have to provide square brackets if I have to first stack the values on top of each other and then side by side. So there's a difference here. You don't need to do it when you're defining it like this, because first the commas are evaluated, then the semicolon is evaluated. So they are going to be side by side no matter what. But here you have to enforce it to be on top of each other and then side by side. So yeah, we have introduced some matrices. There are also some functions to generate matrices. For example, I could want a 2 by 2 matrix that has all entries 1, then I would use this function 1. There's also a zeros. And then there's this identity matrix, which I don't really know what the reason behind this naming scheme is, because, well, as you know, it is called identity, something like this, and there's no function like this. Instead, there's this I, which corresponds to I don't know why. Maybe it's a play on words, I don't know. But yeah, that's another function. Then what we can also have is basically, let me define this matrix here, 3, 4, 5. Now, if I want to look for the length of a matrix, which doesn't really make that much sense, you can see it will give me the maximum of dimensions. So we have 2 dimensions. One of them is the number of rows, one of them is the number of columns, and which one is the maximum? It just returns that. So we have 3 rows and 2 columns, 3 columns and 2 rows, it returns 3. Even if it's going to be the transpose, it's going to be 3, because that's the maximum value. But this doesn't make that much sense. If you want to know what the size is, you should use size, because the size of a matrix makes sense. The length of a vector makes sense, because vector has fixed all the other dimensions and it's just growing in one dimension. So therefore, the length makes sense there. So here, what we can see is Matlab returns basically the number of rows and then the number of columns. And what you can interestingly do here is you can also run this function like this. And if you know what the square brackets means, if you know what the comma means, you would pick up on this, because, well, it means that we have an array of 2 different values stacked side by side. So this is kind of a multiple return mechanism of Matlab that was introduced in Matlab. Now, when you code C, at some point, you just want to return multiple stuff like this. You have multiple dimensions, you want to return the length of each dimension. Now, in that case, that's not possible. What you might do is you might just create an array in C and then stack the values in that and then return the pointer to it, but then you don't know what the size is. Or you could just create a struct and then just put in the values into that struct, then you return the struct, and it has multiple values in it. But in Matlab, we don't really deal with that stuff. We can just return multiple values. Of course, there's no big magic behind it. It's just the Matlab low level of having, again, pointers and then the number of pointers, but it's dealt with behind the scenes. So therefore, this becomes sometimes helpful. And it's basically an important topic that we will, again, touch base on. I didn't talk about the true and false values here. Now, true false is not Boolean or called bool in Matlab, it's called logical. Yeah, I don't know why, but it is what it is. So it's called logical, and we have to deal with that. But fortunately, we don't really need to remember this, because what we do is we just use it, and that's basically it. But I want to show some stuff like the following. Let's have a number and then also true. And what happens if we want to stack them together into a vector? Let's think about that. Now we have a number, 12, and then we have true, but in standard C, as far as I remember, if you don't include stdbool.h, you don't have the Boolean or bool data type, but you can still use if, while, and for, or all the arithmetic or the logic operations that you want. So that's going to be the same case here. Most of the time, we even define an integer, call it 1 or 0. 1 is true and 0 is false. So you should be able to stack them together. And you can. It will just convert the true value into numerical value 1 or into double 1, and we're good to go. Now, I want to see what happens if I also have, for example, a character. Now I have basically 3 different data types, which is not usual for the array. If you think about C, you just define it like, for example, double, and then vector or array, and then you give it a size. What this means is that each element is going to be the same, and it will be of data type double. And what I do here is I'm just combining stuff that is not double, but hopefully if I have the conversion available, it will work. If not, then it will fail. And you can see that there's a problem between the data type logical and character. So what you can do is, instead of using true, when you give it 1, it will work, but not like expected. Now, what happens is that the double is not going to be used, because when we have single quotes, Matlab assumes that you're trying to work with character values. So therefore, we have characters. Now, again, the value 12 as decimal is searched on the ASCII table, and then the corresponding character is here, and then 1, then the character is here, and then A is there. So practically, if I change this to, let's say, 98, it would be B, and we can see that. Now, what happens if I convert or add another thing that is a string? Now we have different values, and then a character and a string, and we want to combine them into a vector. And now this happens. If we have double quotes, everything will be converted into double quotes. Now, the interesting thing here is that we don't lose the data. We're just converting them into double, which is nice, which means that double quotes, or this string class, has more capabilities to it, and it does the right thing that we would assume by default, whereas the character string is kind of more dangerous in this case. You can see we have 12, 98. Maybe this is what I want, maybe it's not, but it still did basically convert everything into a string. So you might ask yourself, what if I wanted to just leave them like that, just conserve the data types, and I still want to stack them together? What you can do is you can use curly brackets and then give them different values: false, true, and then maybe a character A, and then a string ASD. And it would do exactly that. It would preserve the data type. It has kind of its own container, which is called cell, and it builds up an array of cells. So it's going to be a cell array. You can also construct this by using the cell function, as far as I remember. Now, if you don't remember something in Matlab, this is the nice thing about Matlab, because you can ask Matlab for help. And if you know that command, and if you don't remember it, then you should use help, because it assumes that you know it, but you don't remember it. So you have to be working with it before. But if you want to learn it from scratch, then you're looking for the documentation. So you should call doc cell, which will pop up your window. And in this window, it will give you much more detailed explanation about the code, what it does, what it is for, and what some examples are, etc., etc. Here we can see it shows you the creation, that you can create like this, and then you can use it like that. It has some special cases, some arguments, input arguments. It tells you all the things that you might want to know. It has also some tips and tricks, and it also gives you some related functions list where you can again click. There are also some topics that you might be interested in. So it's quite powerful to have this documentation available to you. Now, let me show you something else. if I open up a browser page, if I come here, go to Google and say MATLAB and cell, and click on the first link, which is MathWorks website here, you will see that you're greeted with the same page, same data, same thing. So the nice thing about this is that basically you don't really need the internet itself. You can close this because this data here is available offline on your computer when you've downloaded MATLAB and set it up. So since we are all students, you can just assume that even though you don't have internet, you just need MATLAB if you are trying to ask something. Except that you're looking for Stack Overflow or stuff like that. That's another story, of course. Now, cell array doesn't really make that much sense, in my opinion, because, well, if you're stacking stuff together, you should be the one to know which one is what, and it doesn't really give away that much about the data itself. You can just forget about it, and then you can mix up the stuff because we have two numerical things here, and I don't know which one is what. So a better approach to this would be the struct, which is basically based on the C-type struct, which you can create in C, or which is the bare bones of object-oriented programming. Now, but the difference here is that you don't need to create a new file. You don't create this whole mess in C. You just have a function that constructs you a struct with the field names and values. This is kind of the Python dictionary equivalent in MATLAB that we have here. And what you can do is you can probably do something like, let's say age, for example, age, let's say 25, and then you can have some name, which is going to be Bob, for example, and then you can say, I don't know, child, and then true, something like that. And there we go. Now you have created maybe not this cell struct here, but you have created a struct, and the struct gives away much more data than you would need, because you know what the value is associated with what, or what its meaning is. So this one makes more sense. And the application in our course will be that struct, we will encounter structs most of the time, and we will use this to distinguish numerical data from it. As far as I remember, the step info in the control system toolbox gives us a return of data type struct, where we can then see what the time domain values of a step response is, for example, setting time, overshoot, etc. Those are going to be the field names, and then we have also the values according to them. Now, this cell here is also, it has also a use in our case, which is going to be the body command, as far as I remember, because if you have a multi-input, multi-output system, a transfer function, then there will be multiple channels between inputs and outputs. And you might be interested in certain input to output transfer functions. So that will return us in a cell array. And transfer function matrices are also defined as cell arrays. So you can see it should be something that has multiple input, multiple output channels, which makes sense to use cell arrays. So yeah, structs are quite easy to construct and use. It will be also important for our probably for our homeworks or quizzes. So knowing how to define a struct or accessing a struct's fields is important. Let's say this is a person. Then what we can do is we can use, again, this dot operator, which is the same in C, dot name, dot age, dot child. These are the fields, and we have a string return, a return of a double, or we can return the logical value 1, which might be useful or something. If you're advanced enough, you can embed functions into this one too, but that's not that important for our topic, so I'm not going to touch base on that, but you can do it basically with this single call of struct function here. Yeah, that's the struct. So let me check out my PDF. Even though I didn't open up my PDF that much, I'm basically following the topics here. So we've talked about this. Now we are at the conditionals. Now there's not too much to say about the conditionals and loops. What I can just talk about is the following. We need to basically have true in order to work with this if block here. So if this is, for example, false, if you have disp, which is the short for display, what we can do is we can just say ASD, for example, and then there we go. So if we run tests, you can see we can see nothing. And the reason behind that is this one was true, so the execution did enter this if statement here, if block. But then, since this is false, it didn't enter here. It jumped to this one here. What we can do is we can just say this again, and then check out if it's working out. Let's say AD for some reason. When you hit F5, you can see that it works. It will run the script here, and you can see it jumped and it didn't execute this one here. You don't really have to use true or false. It could also be 1 and 0, which is interpreted as basically true or false. So I'm running it and it doesn't change. Now, this is not that quite interesting. We have this if-else structure here, but it is only about this condition here. So when we have a condition here, condition 1, cont 1, and let me get rid of this. So the problem, or the main thing about this is that we have this condition here, and else is basically another if check on this condition, but on its logical not. By the way, we don't use exclamation mark, we use this tilde here in order to take the logical inverse of a certain logical thing. So this is basically if else, and if you have multiple conditions, then it becomes more tricky and also more useful to use else if, because you might want to take some action on condition 1 and condition 2 being true, but then another different action on just one of them maybe. So condition 1 or condition 2 could be the case that you're looking for example, and then the rest of that could be of interest. So what you can do, instead of writing down multiple ifs and ends and stuff like that, you can just combine them into just one if, else, and end. Yeah, this is basically if, and if you use if, it will become more and more clear. I cannot talk too much about it, but what I can show you is the following. For example, if we have an operation like this, and if we display this value, for example, by the way, you don't have to convert stuff into string when you use disp. You can just provide it any data type and it will convert it automatically. And let's basically increase the value of it. The only downside here is that we don't have this plus operation. I really miss it in Matlab, but I don't know why we don't have that. Maybe it's about the pointer structure that has that is behind the scenes. But yeah, I would really like to have that here. But yeah, a is equal to a plus 1. Now, if we run the script, you can see it will give us the output 1. So this is not that exciting. But what is the following. I can just copy and paste them, unlimited amounts of if and else, or the if block itself. I can just copy and paste it as much as I want. And if I run it, I can see that it stops at a certain value. And the reason for that is the following. I use true and false to show you that it works just if it's true. Of course, true on its own doesn't make that much sense. But if the condition is not true anymore, that's a whole different story. I can just initiate a certain value with a variable. I can then have this display function, increase the value. Once I hit on this false condition, which would be 3 is not less than 3, it is less than or equal to. Therefore, it stops working with 2. Once it's 3, 4, it gets just worse and worse, but it never enters the block here. So therefore, this is kind of an alternative implementation of the while block. I don't really have to copy and paste the same code over and over again, where I can just use a while here. So basically, I'm going to erase this and put in a while and get rid of all these if blocks here. But the machine code implementation is basically this. It just jumps from a certain point of the if to the condition here. With the updated values, this is checked over and over again until this is basically violated. Now, if that doesn't happen, if I probably, for example, don't increase the value here, it will stay less than 3 and it will become an infinite loop. So it is dangerous to toy around with these. So this is basically the implementation of a while loop, and it will do basically the same. Now, we have talked about if and while, and it doesn't matter how much I talk about it, it is important to practice this. So it's going to be upon you to try to solve the homeworks and quizzes and stuff, and hopefully you will learn more and more MATLAB, because you need more and more MATLAB. So let me also talk about the for loop. But in my opinion, I would say that the MATLAB for loop resembles a for each loop more than a for loop. And the reason is behind the syntax, because what we have is we have, for example, this syntax here, which is going to be doing the same here. It will start with 1, it will stop at 2, and it will execute it for the values that are available here. But my issue with this, and let me first run this and show you that it works exactly the same, is this operation here. We didn't talk about this colon operation, but this colon operation is kind of generating a vector out of series. So you have a starting point and a stopping point. The increment is 1 by default, and it creates you the vector. So you can just create a vector of values using the colon operation with increment 1. You have a starting point 1, stopping point 20, and you have a vector. And you can also see that this is a vector because you have a 1 by 20 double in the answer variable that is defined automatically. So what you can do is you can give it a certain increment value of, for example, 0.1. Now you have a 1 by 191 vector of values. So, and the reason why I'm saying that this is basically a for each loop is that it just takes 1 and 2, because this is basically the same as writing down colon. So instead of doing this, I can also do this, which is basically the same. So we have a vector here, and then we have kind of the element of a vector. So for element E in vector V, this is kind of the approach that we have here for the for loop. So it's kind of a for each loop, because A will be each value in the vector that is provided here. So therefore, it's kind of not the C version for loop, in my opinion, but it doesn't really matter because we're in MATLAB, and yeah, you will use for like this, and it's just going to use vectors. What you can do in order to be a more C type of a guy is you can use a length, so an index-based approach here, where let's say A is the vector itself, 1, 2, let's add 3. Let's get rid of this. So you can do this, and then you can have probably the ith element of this, and then run this, and you have a for loop kind of thing here. Now we have the indices. But for just one vector, using this for loop is not really that important. But if you, for example, create another copy of it, let's say zeros 1 by 3, and if you want to do something on it, bi is equal to ai something, I don't know, maybe times 2, and then you want to, for example, use bi or something, then it might make sense. Although for most of the signal processing applications, this would make sense. For vision-based stuff, this would make sense. But for basic operations, this doesn't make that much sense, because we've seen this already with the example ASD plus ASD. These were vectors, and what we can do on vectors is the following. Even though I have 1, 2, 3, I can just say I want to add 2, 2, 2 to this vector. And this shouldn't be possible, but it is possible in MATLAB. Also, the following should not be possible, but is possible in MATLAB. There we go. And it basically creates the same result here. So most of the time, this is powerful, but somewhere in our course, this will be dangerous. And the reason is the following. You have to be aware of this phenomenon. You have to be aware that MATLAB can do stuff element-wise. And if it does, then it will change your perspective of MATLAB, because you can do vector plus scalar, which is not possible mathematically, but it is assumed that this is an element-wise operation. A vector plus vector element-wise should not be possible unless you use this for loop here. So what I mean by this is you should have 2, 2, 2, and then C, which should hold the result. You will go one by one, take A and add B to it. So this is kind of the C version of this. And then you will see the result C. This is the whole thing that you should code in C in order to get this effect, because you have a piece of memory there, a piece of memory here, and then another piece of memory that you need to create in order to hold the answers of element-wise plus operation, and then you should store that there. So that's the whole thing that we do in C, in low level. But here in MATLAB, what we can do is we can just on the fly create a vector, give it another vector, just use a plus operation, and we can avoid using for or while or any loops. So this is kind of the power of MATLAB, and you can just use the plus operation and you are good to go. You don't really need to use for loops. Let's say you want to add a matrix. What you can do is you can add a number to a matrix. But keep in mind that it is an element-wise operation. So each element is added 1. This is not the same as, which is the dangerous part now. This is not the same as using identity. So you have to be aware of that. This is matrix summation, but the previous one is basically an element-wise operation. For plus and minus, you don't really have to do anything else than using plus and minus. But for multiplication, for example, I'm going to show you that we need to do stuff. So let's say 1, 2, 3. I want to multiply it with 2, 2, 2 for some reason. Of course, I cannot do that because 1 by 3 times 1 by 3 doesn't work mathematically. But I can use a for loop. I can use an element-wise multiplication. That is a different story. What this does is it just takes the first element of the second operand and multiplies them and puts it into the place there which it should be. Then 2 times 2, so 1 times 2, 2 times 2, 3 times 2, it is going to be 2, 4, 6 in a vector. So this is quite powerful because what we can do is we can also divide element-wise. There we go, 0.5, 1, and 1.5. And we can also do crazy stuff like this. We can have the sum here. And if I run it, even though this one here runs, and I'm going to get rid of that. There we go. So it divided each member into 2, and then the resulting vector's elements sum is then produced here. So you don't really have to use a for loop. You can avoid it most of the time. We have also this product function, which just takes the multiplication of values, and you get the value here. This sometimes is used for example, element-wise square, and then the sum of that in order to have a certain metric, and you can get this result, basically. There's also the fact that we can use mathematical operations. Let's have 30, 45, and 90 degrees. We can also use them. Of course, this is not the correct sine function because this is in radians. If you want to use degrees, you can just provide an extra d here, and you can see 0.5, 0.707, square 2 divided by 2, and 1 are the values, and then you can just maybe take the sum, the product, whatever you want to do on it. So this is quite powerful. Usually what you have to do is you have to just calculate each of the elements and then put it back in a vector or just accumulate them on some, etc. But if you really have to use the for loop or while loop, then you're going to write a for or while loop. Other than that, there might be functions in Matlab called sum, product, or element-wise operators that might take care of the operation in a much faster and simpler fashion. So, well, we've talked about this. There's this disp here. I've shown you that we can basically add two strings to each other, but let me show you an application of that we might want to use. Let's say we have a equals 2, and I want to display a is, and then maybe, or the value is a, and then the number of a, or the value of a. So what I do, because this is a vector of characters, I'm going to comma separate it, and then I'm going to use num to str as a function, which takes the numerical value, converts it into a character. So I can just use this approach in order to generate this message here, and then I might display it on the title, maybe on an x-axis or somewhere that I need to do. Even though this is called string, this is not generating a string, and the reason behind that is basically the C-style naming of stuff. There's also sprintf or fprintf in Matlab that you can use exactly as you expect it to use. But the difference here is that if you use fprintf, it will just directly output it to the console. So like this, and then %d, and then maybe a. This is also possible, you can see, but this is the console output, whereas this is going to be a value assigned to a variable here. But if you use sprintf, it should be basically the same here, as you can see. You can use sprintf too. Now, fprintf can be used with files. If you have a file ID, like it is in C, you fopen and fclose a file, and then you can just write into a txt file, by the way. So another version of this would be with double quotes, and let me quickly show you that, other than sprintf. And that would be just adding string a to it, because this will convert a into a string. Now, there we go. Of course, you can also cast this into a string or this into a character array, but that's not really necessary because both of them are strings. So that's that. We've talked about if, for. Now we are going to talk about functions, and then we can conclude basically the basic MATLAB discussion. And then I'm just going to touch base on the symbolic library that we will use, and then a little bit about control system toolbox, but it will not take that much long. So yeah, let's dive into the functions. Now, defining functions is quite important because, well, sometimes it is necessary, but it will also demonstrate to you the fact that MATLAB is an interesting language, since it is very flexible, very useful. Writing functions, we will see. Now, talking mathematically, when we want to create a function, like take the square of something, which is not really relevant, or which is a trivial example here, this is basically the way of using the function, because we've used functions. Here's the function call. Here are the input arguments. We can have multiple of them, doesn't matter. And we will have then the output here. So I'm going to take this, create another script, use the keyword function, and then place and we're good to go. I'm going to save it. And when you save it, MATLAB recommends you to use the same exact name as the function has. And yeah, that's basically it. If you pay attention to the icons here, you can see that this has kind of an FX here, and this is kind of a script because it has just MATLAB on it. So this is a function, this is a script, so they kind of are different. And well, you have basically defined your first function. And what you can do is you can just say y is equal to x times x, and you can then use take square and then maybe 3, and voila, it works. Well, this is not the whole story, of course. One big issue with writing functions in MATLAB is that you have to really pay attention to the input and output arguments. For example, we don't have any assumption on the data type of X. So what could happen is someone could enter a string into it. And of course, it doesn't make sense to multiply a string with itself. Therefore, MATLAB complains, but your function doesn't take into account what the data type is. It would also be an issue if we have the character array, but I would doubt that it wouldn't be an issue if you have a single character. And the reason behind that is that the single quote A corresponds to a certain 7-bit value, and then that value is just converted into double, and then we have the square of that, which still doesn't make sense, but we have to check the data types. And yeah, we also have to check the size of the input, because it doesn't make sense to input a vector like this, but it would make sense to have a matrix, for example. So it becomes complicated to have a function that is as flexible as the MATLAB environment itself is. So therefore, you have to take care of such stuff. For example, you can check if this is basically double. So let's say we want to just do it when it's a double. And let me clear, let me CLC, and let's try this one here. So you can see it doesn't do anything now. And the reason is that it didn't enter this is A and then X double, because it's not a double. But if it is 1, then you can see it returns us the value. So what we can do is we can just have an else, and then we could display an error message complaining about this. And therefore we have a function that is neat. Type not supported, for example, would be a good message here. And then the type is going to be string. And then the type is going to be class of X. So this assert function, if you don't know what it does, this is basically assertion, and it will complain, or it will throw an error message when the condition, which is the first parameter here, or the expression, returns false. I, by default, just return false, then this will automatically be asserted. This will always through an error that is going to be this message here with the error message that I've generated on my own. So when I, for example, run it like this, then you have this MATLAB type error that says using take square on line 5, type not supported char. So then I notify the user that basically this function is not compatible with using the char. But then we also might have some other issues. For example, it could be a vector, it could be a matrix, or it could be a scalar. So what I would do in that case is I would just say, let's try to look for the size of it. Now, before we do this, we have to call our function m by n, size, and then x. Now, if m is equal to 1 and n is greater than 1, or, so in order to be consistent, I'm going to say that this is going to be condition 1, and this is going to condition 2. If m is greater than 1 and n is equal to 1. So in that case, I'm entering the vector case. So this is going to be vector. Else, I'm just going to return this one here. So for the vector case, I might be interested in the element-wise square. So this would be a nice solution if I'm going to take a square of certain stuff like this. So this works. Basically, 1, 2, 3, 4 works. If it's a scalar, it works. If it's a matrix, it does work. And if it's going to be a vector, now I have element-wise square. So this is kind of neat. And yeah, this is kind of a good solution. We just use double here and nothing else. We check for the size, and then we have an element-wise square for the vector, or we have the matrix multiplication. So yeah, sometimes we might want to have some multiple inputs for example, extra data. So what we can do for that is we could have another variable. Let's call it, I don't know, maybe case. So case, let's say that this is going to be case 1. So if it's basically entering here, it's going to be case 1. And if it's entering here, it's going to be case 2. I don't know, I just came up with this. Just some extra info for debug, for example. I can also return that. So what I can do is I can just say case, and there we go. We are just going to return another thing. And this works like the size function works. Now let me just enter a certain value. Now we can see that for some reason, if we enter a scalar, we have case 2, and it's going to be evaluated to 4. You don't really have to call it like this. What you can do is you can just call it like this, and it will give you the first output argument that you're interested in. So it's priority-wise ordered. So this would be the first one here, and you can have as many outputs as you might want to have. So you can have these many outputs, and if you're just interested in the first one, just call it like y equals take square, and that's going to be it. So this is the power of multiple return mechanism that I've talked about here. And it sometimes is important. And as far as I remember, for example, the step function, it returns y and t, and you might just want to skip t here, or you might just want to be interested in both of them. And you can do that. And this is basically multiple return mechanism that is important for functions. You can also count the amount of inputs that are provided. So this is take square, but what happens if I don't have any input? Well, then the function says not enough input arguments. But this is the job of basically the person who is coding this function here. So how can we check how many input arguments there are in Matlab? Well, we are going to use narg_in, and if it's equal to 0, for example, we can say that should be 0. Let me put it under double here. So there we go. So if it's that, then let's have this always here. And yeah, so else if would be then narg_in 1, for example, then we would do this here. And once we're done with that, we would then use else and then and. Now, the more nested stuff you have, the more important becomes the indentation here. Since we're not using any brackets, any curly brackets for beginning and the ending of a block, or any usual brackets for the conditions, here I'm going to use it when they're necessary, but when not, then you don't have to use them. You have to indent them so that it's more readable. This is kind of a Python thing. It's also valid for Matlab, so keep your indentations to have more readability. Here I can say I'm checking if it's a double. If no input arguments are provided, just return 0 for some reason. If it's provided, calculate it and then return it. Otherwise, just maybe again assert or do something else. It doesn't really matter. Let's say too many input arguments. I don't know, because I don't want to deal with them now. Too many inputs. That's it. So there we go. Now, when I use this without any input, not enough input arguments. Is double. Oh, since that's not available, we should basically place it here. There we go. And then this goes one more in. Then we're going to have int. There we go. Yeah, because we've ended it. Oh no, actually end. Oh, we have to take this in here, I guess. So yeah, there we go. Now we can have no inputs at all. We return 0 when we have a certain input, when we have something invalid, or when we have multiple inputs. It's just going to say too many input arguments. And there we go. I'm not quite sure if we're asserting with too many input arguments, too many inputs. There might be a reason to that. Well, I don't know. Oh, maybe I should. Oh, okay. Else if narc_in greater than 1 makes more sense in this case. Else, I don't have anything for else now, but interesting. We couldn't kind of override the thing here. Narc_in is greater than 1. Interesting. Maybe I'm missing something. But yeah, this is the way of using the narc_in. And if there's no input argument, you can just take care of that. But the whole story here is the following. In Matlab, you can have functions that have multiple inputs and even multiple returns. But if you're coding your own function, then you should be really, really careful, because one expects the flexibility of Matlab. And if you're providing someone the function, then they will also expect your function to be almost perfect. So keep that in mind. Try to think about all the possible inputs that might be of interest. And if they are not, then you should also notify the user that you don't really work with those data types or many inputs, etc., etc. Now, this was kind of a survey of the basic MATLAB knowledge that you need for this course, and I think I'm done with the whole introduction of MATLAB. But the interesting thing about our course for our laboratory sessions especially is the fact that we are going to use MATLAB in a bit more different way than we use it in our daily lives. And the reason behind that is the following. We are going to discuss the theoretical aspects of control system design. And when we're talking about design, we will have some theoretical stuff. We will have some algebraic operations that we need to take care of, or calculation of formulas. Therefore, we will use the computer assistants here instead of using pen and paper or maybe a scratch board or something like that. We're just going to work on MATLAB. We want Matlab to take care of the design steps here. That is a bit different than having basic Matlab knowledge. For this particular reason, we were using actually Mathematica in the early days, but we have seen that the perspective of Mathematica is kind of different and difficult to grasp within the context of this course, because there's this problem of interfacing Mathematica, and then there's also the problem and the difficulty of the design problem itself. And these two don't really go well with our students. So we ditched Mathematica for that reason, and we opted to the MATLAB symbolic library, where we also do our simulations. Why wouldn't we use MATLAB for this particular reason? But the issue here is sometimes the following. It is most of the time not that powerful as Mathematica, but it does a good job. So Mathematica is quite powerful in handling symbolic algebraic operations, but MATLAB is also good. So we are going to use MATLAB symbolic engine here. And what we really want to do, instead of having this function, instead of having this value-based variable definition where I say a is equal to 2, what I now really need is I need basically something that is going to be a variable, which is basically a symbolic variable that I'm going to try to manipulate on MATLAB. So for that reason or purpose, I can just have some symbolic variables. And since they will not have anything as values, I can just define them with the keyword symbols, basically. And now I have actually declared some symbols. When I run this, I can now see that in my workspace, I have sims here. And the beauty of this is that I can construct some polynomials, for example, but in fact, these are just data structures, and these data structures help us out in defining the problem in MATLAB during the design step, and then try to solve it. And once we've solved it, we will obtain some numerical values, some controllers, and then we will have a system, and we will plug them in and use the control system toolbox. But before that, we need the design steps in MATLAB. So the good thing about this is you won't be using pen and paper that much, because you don't have to carry out the operations yourself, unless you're in a classical exam. So therefore, we can just provide MATLAB what we want. For example, we have an expression that is SQ plus 2S plus 1. And this is no ordinary variable or expression, because it is a sim structure. So this is a internal structure of the symbolic toolbox, and it handles stuff for us. It will know how to handle these symbolic operations for algebraic operations, especially. So what I mean by that is, for example, the following. When we have a transfer function, it would look like this. So let's have that. And there we go. This is a certain transfer function. But of course, this is not a transfer function at all. This is just the symbolic representation of a transfer function that we're interested in. For example, I'm trying to design a controller to this transfer function. So what I really need to do is I need to, for example, convert this into a transfer function object for some reason, because then I want to apply step to it. Now, you cannot do this. This would be nice, but it's not possible. So GSS step and run this. It will not work, because this belongs to the control system toolbox. This is in the symbolic toolbox, and they don't work with each other. In order to do that, what you usually do is you just define a TF object, which has basically the coefficients here. You would have 0, 2, and then 1. Drop this one, run this, and there we go. It should generate the step response of the transfer function that I've already defined here. Hopefully. Yep, there we go. Now, we sometimes need the transitioning from symbolic toolbox to the control system toolbox and vice versa. And it's a good exercise to show how we can manipulate stuff here. For example, this is a basic fraction, and I can just convert this fraction into, or I can just take this apart into its numerator and denominator. So num.gss is a symbolic function again. It's another function of the symbolic toolbox that takes in an expression, and if it's a fraction, it will return you the numerator and the denominator. So let me run this part here. Now you can see there's ns and there's ds. So I have the numerator and denominator. So what I still want to do, if I want to convert this, for example, into a TF object, is I want to get the S coefficients here, because all I'm interested in is the S coefficients. So for that, we have coefs, which is, again, another function. And I can give it an expression, and it will calculate me the coefficients here. For the numerator, we can have these coefficients here. For the denominator, we can see that these coefficients are not quite correct. And the reason behind that is basically that this is basically a symbolic expression. And the data type behind the scenes is a tree structure, which will decompose this expression into its elements. And once I call coefs on it, it will just take this as an expression, and the coefficient is going to be 1. This is an expression, and here the coefficient is 2. This is another expression, and the coefficient is 1. So therefore, it returns me 1, 2, 1. But as a control engineer, in the sense of a root table or for this TF object, I always, in my mind, expect the coefficients to look like this, because I think about the ordered highest order to lowest order coefficients of a polynomial, because I cannot reconstruct the polynomial in my mind, because we have 4 here. It will start with s to the power of 0, s to the power of 1, s squared, and s cubed. So this should be s cubed plus 2s plus 1. So there's a standard behind the scenes here that we all agree to use. So therefore, I want to stick to that. But here, using coefs on its own doesn't do the job, doesn't cut it. So what can I do now? Well, there's also an interesting opportunity that we might have also some hidden variable k here. Maybe a controller parameter k. And when I look for the coefficients, you will see that, for example, if you expect to have 1, 2, and 1 plus k, then you're not correct, unfortunately. Because again, this is a symbolic expression. Behind the scenes, we have the tree structure. It will decompose it into its sub-elements. And these are basically the sub-elements. The coefficient of s cubed is 1. The coefficient of 2s is 2. The coefficient of 1 is 1, and the coefficient of k is 1. That's the reason why we have 1, 2, 1, 1. But we can explicitly say or tell coefs that we want to have only s coefficients. Then we are on a better track here, because then k is treated as a coefficient, not the symbolic variable that we're interested in. Therefore, it returns us k plus 1, 2, and 1, but still not the structure that I had in mind, because when I reconstruct this in my mind, it would look like k plus 1 s squared plus 2s plus 1. That's not the polynomials that I'm looking at. So therefore, I need to provide a third option that is called all, which will then assume that we will have the highest order term, and it will complete the missing parts, because we are missing s squared here. That's not in the tree structure. Therefore, the coefficient is not calculated and it's not returned. But the symbolic engine behind the scenes has to just look for the highest order and then maybe construct a vector of the according size, which is 4 in this case. And then it will fill out the corresponding indices here. And since we don't have s squared, even though we don't have s squared, the vector was pre-allocated, so it will have the value 0 that we're looking for. So when you're using coefs, you're going to use it with these extra options. It's going to be s if you're looking for the coefficients of s, and you can provide all in order to have the right correct ordering and the standard that we're looking for, because I can reconstruct this. It would look s cubed, 0s squared, 2s, and then k plus 1. Now, still, we are not done here. Let me just for the sake of being correct here, let me define them like this. Now, if I run this, you can see there's nothing double in here. So what we do here is basically we're communicating with a symbolic engine, something like an AI engine or a game engine. We're just communicating with that. We are using the Matlab language and we have certain functions, but we're just communicating with that. So therefore, it's kind of like a Laplace or Fourier transform where you have the problem in the real world. You're just defining this problem or converting this problem from the numerical world into the symbolic world. You solve it there, but you're still in the symbolic world. You didn't convert anything into double. You didn't convert anything, even though you have something that resembles maybe double for ns equals 1. And the reason is going to be explained in a minute, but what we can do is we can force it to be a double. And then magically, you can see the enforced version gives us a double, but I cannot do it for both ns and ds. And the reason behind that is k. Because we have k here, which is a symbolic variable, which is not associated numerically to anything, the problem is that we cannot convert it. So what we have to do is we have to get rid of it. Of course, in this case, I'm just going to delete it, but otherwise we can do stuff to it, and I'm going to show that in a minute. But now, when we enforce them to be doubles, we have returned to our domain. So let me just convert both to double. There we go. Also another one, the s term here. If I run it, now we have ns and ds. Now I can just provide this to, or feed this to these functions here. This is going to be ds, this is going to be ns. Run it. I guess generated it. There we go. If you want to see the effect, what we can do is we can just make this to an s square. So now it works. And there we go. We have this nice step response. Now, you might say, why didn't we just define it in the as a TF object and moved on with our lives? Well, because we are going to replace this first part with control system design. I just wanted to show you that we're going to start with a symbolic toolbox probably, solve the problem, obtain the PID parameters or the P controller or whatever, and then convert it into TF objects and then immediately see what the result is. The power here is that I can just change it in the S domain and it will have effect all over my script and it will convert it into TF object and it will verify it. So that's nice thing about that. What we also can do is, let me just define a certain controller parameter. For example, we can have the keyword real if we want to define real values. Doesn't really matter at this point, but we have some additional stuff that we can do here. And let's say we have the controller k, and we want to just calculate the closed loop transfer function. Then we have k times GSS, and then this whole thing divided by 1 plus k times GSS. Now we can use TSS in this case, and this would be then TS and then the step response of that. So now, of course, somewhere here, we will get an error. And the reason is that we have this symbolic expression TSS, which looks like the closed loop, but which is not readable that much. Now, if you have this issue, you can use simplify. TSS, or there's also something called simplify fraction. We can just choose them. And you can see now it looks more like it. And once you've done that, what you can do still is to call this pretty function, which tries its best to prettify the output. Now it looks like a fraction that we can read even better. Now this is going to be my closed loop here. The only thing that is missing is that I get the coefficients, but the coefficients have some symbolic terms in it. Therefore, it cannot convert it into double. So this is my issue here. But I can basically use a function called subs here. And this stands for substitute. I can provide it the expression. And then the symbolic variable that I want to replace, because I want to do the following operation, for example, k equals 1. I want to plug in k equals 1 here. So if I want to do this, I can just take TSS, because this is the expression that I'm interested in, have k, and then the new value of k should be 1, and I can substitute that. Now it will work with the value that I have in mind. Now you have the closed loop transfer function with the p-type controller k equals 1. And you can, of course, use a for loop to check stuff like that. Or there's an alternative way, which is going to be an advanced thing, but I like to use that nowadays, is that you can have a Matlab function for this transfer function. And it will be called Matlab function. And this Matlab function is going to take TSS, and then you will have some variables, S and K, and then you can use this instead of using this substitute method here. I'm just going to leave it here and not execute it because I don't want to confuse you. But the problem with subs is that if you are substituting vectors with length that are quite huge, then this operation might become a little bit slower. Instead of doing this symbolically, most of the time, converting this into a Matlab function optimizes your code basically, speeds up your code basically. And since most of us don't have the best computers in the world, we sometimes need to use Matlab functions instead of the subs here, because subs is just doing it all in all the correct ways. It just substitutes everything one by one in a symbolic algebraic manner. But sometimes that's not what we need if we want to have some performance out of it, because we will have nested for loops and then substitutes in them. So yeah, sometimes optimization is important. Now, this is an advanced thing, so therefore this we can skip that. But I'm about to conclude my introduction, but let me ask you a question, an important one in terms of computer science, because all we know is that computers work with base 2 numbers, so binary values 0 and 1s, and some divisions for the floating point units are quite difficult to carry out. And one of them is 1 divided by 3. Now, and you can change the format of MATLAB to long. If you do the same operation, it will give you more precision here. Now, my issue is the following. Let's say this is going to be my new value, x. Now, if I input 3 times x, I will get something that I don't really expect, but is good to a certain degree and bad to a certain degree. Now, if I input 3 times x, you can see that MATLAB gives you the correct answer because x is not equal to 0.333, it's equal to 1 divided by 3, which has a difference. Now, but if I, for example, if this would be the value of x, if I multiply it with 3, you will see that this is not exactly equal to 1. And this might be looking trivial for us because in computer engineering, most of the times, if you don't leave Earth, this doesn't make that much of a difference. At least it doesn't come up to my mind immediately. But if you're working with high precision or very, very big numbers, these types of precision problems become quite important, because if you're trying to land on a planet, you might even miscalculate it so that you're not even on the right planet or even near it, because these are rounding errors and these are floating point errors, which we don't really want to have. Now, MATLAB does correct this behind the scenes. by having some extra stuff here. But we can also do something like 1 divided by 3, but symbolically. The power of the symbolic toolbox comes here into play because we have the value 1 divided by 3. And when I multiply this with 3, of course, it will be equal to 1. This makes more sense than having a representation that looks like 0.3333 and then calculating or just multiplying that with 3. There's an inconsistency here. You can see that this is kind of an approximate value, whereas this is actually the value that is behind the scenes stored. So that's basically important. But what happens if we have, for example, sims k, and we have k divided by 3? Now, of course, it looks like k divided by 3, but sometimes you want to see what it would look like if it's more readable. And you can do that by using the VPA function. It stands for variable point arithmetic, something like that. And it will give you the numerical parts like it would be in double, but then there are also the symbolic expressions here. Sometimes these types of shortcuts will save you in terms of readability or understanding the expression. So yeah, this becomes handy because we can have a solve command here. We can solve some equations. Let's have sims x and y. For example, let's have x squared minus 3 times y equals 2. And then another equation, maybe x plus 2 times y is, I don't know, maybe 4. And if we want to solve them, now keep in mind that I'm using double equal for defining an equation, which is possible here. So we can do that. Let me just, there we go. This is now an equation. If I get rid of the semicolon, I can see that this is basically an equation. So we can define polynomials, equations, all sort of expressions symbolically. And the nice thing about this is that when we want to solve it, we can just stack them in a vector. And we can expect the solution here. So what did we do here? So somehow we messed that up. There we go. Now you see that we have a struct here. So it returns us multiple values. And the solution of x is given symbolically. So you can force it to be double. Again, you can convert it into double. It will give you the numerical representation here. Let's convert it into short. You can see 2.17 and minus 367 is kind of the solution here. Or if you don't want to force it, you can maybe use pretty and then solve at x in order to see what it looks like. Now we can see it's minus 3 divided by 4 plus minus square root of 137 divided by 4. That's kind of the solution that we can see here. So in the symbolic toolbox, we have to keep in mind that we can enforce accuracy here because 1 divided by 3 is going to stay as the expression 1 divided by 3. And we can have lots of expressions and we can deal with them. It's kind of a way of communicating with the sim engine and trying to solve our problem using the sim engine. Now we have some functions, a list of functions that are going to be used most of the time. We can define polynomials like this, which I've already shown. This is the most important one because we will use this to convert or get the coefficients of a polynomial. If you're a little bit lazy and you don't want to really type it out, you might want to provide a string that is then going to be converted into an expression. This one I don't really use that much, sim2poly. Here we can see that we can store the coefficients and then we can look for the roots of the coefficients, whereas we can also solve the polynomial equals 0. Both of them can give us the roots of a polynomial, but you can use either one of them. And I have talked about subs because we have an expression, we have the symbolic variable, and then the new value is going to be plugging in that value into that polynomial. Simplify is important. Sometimes it's simplifiable. For example, cosine square plus sine square is just going to be 1. This should return you 1. Simplify a fraction, x squared minus 1, x plus 1. This should be x minus 1 if simplified. So that the simplify is kind of important. Coefs is kind of important. And on the way, you will learn it and it will become second nature. The more you use it, the more you get used to it. So therefore, homeworks and quizzes will be around that. Now, if we have a certain expression, but we still want to have it readable, we use variable point arithmetic and give it some digits, and it will show us like that. Now you can see there are lots of other stuff, and you can use the MATLAB help and doc commands in order to learn more about them. Expand, collect, combine, factor, they are just some of the functions that we might want to use. So I've talked about this stuff here. Also, I've shown some of this code here. So we kind of completed the 1/3 part of MATLAB, which is MATLAB's basics. 1/3 part where we are talking about the symbolic engine. Now, the last part, which I'm not going to go too much into detail, is the control system toolbox part. Because the lecture is called control system design, we need the control system toolbox, obviously. We can define a transfer function object, which is basically going to be the transfer function representation. We can convert it into its zero, pole, and gain representation. We can convert it into a state space format. We can use the feedback command in order to have a unit feedback connection or a feedback connection. We have step and step info for time domain data, LSIM for different types of inputs, body for the body plot, which will become relevant in the frequency domain, PZMap, RLocus, etc., etc. And you probably know also already how to use TF, ZBK, feedback, and this sort of stuff here. I've talked about this because this can return you basically the T and Y values for the step response, and you can just plot them yourself. And we have here a basic example which can form a base for our weekly laboratory sessions. So we start with the symbolic engine. We have something in mind. For example, what happens if we have a divided by s plus a, where a is going to be varying from 1 to 5. Now, what we do is, even though this is not the best and optimized code or even necessary, this is a trivial example, but still to exemplify, we have a divided by s plus a. We decompose it into its numerator, denominator, convert them into polynomials, and then basically this will return coefficient vectors. And then just define the transfer function, apply step to it, plot it, and then show the plot. So this is kind of the bare minimum code that we might going to code in our weekly laboratory sessions. So there are 3 parts to MATLAB: basic MATLAB, a control system toolbox, and symbolic toolbox. If you are missing parts here, if you don't feel knowledgeable in any of them, you can just check out the documentation and you can just try the weekly stuff that we are going to do. And I believe you will just catch up as soon as possible, probably. So this basically concludes our today's introduction. It was a very heavy and everything at once type of laboratory session, but yeah, that's kind of the nature of the introduction week of our course, because we have too much to cover and we start from bare minimum, bare basics to the full complete set of MATLAB that we need here. Hope that this was helpful for you, and yeah, we'll see each other next week, same day, same hour.